Hi again, everybody, and welcome back. All right, so this is example 10.8. This is going to deal with a bullet and a block being fired through it. So let's go ahead and read it real quick, and then we'll set it up. And what I'm going to do is actually give you sort of a three-step process for solving this. So let's just go ahead and read this. A bullet of mass 75 grams. So actually, first of all, what we want to do is turn that into kilograms, right? So 0.075 kilograms. Is fired with an initial velocity of 450 meters per second. All right, so it's traveling at 450 meters per second at a wooden block. All right, we have the block's mass, that is 2.25 kilograms, and it's at rest. All right, so the bullet, that I should say, it is the bullet, it emerges on the other side of the block, traveling with a reduced speed of 125 meters per second. All right, so but the block is also moving too because the bullet has hit it. So what happens is the block starts sliding, and because of the coefficient of kinetic friction, which is stated right here, it will slide some distance before stopping, and that's what that is asking us right there. Okay? So here's what I suggest that we do, kind of as a step-by-step thing. A. Solve for the final velocity, for the final velocity of the block, which, by the way, B is going to be the bullet. Block also starts with B, but I'm going to say W for wood block. All right, so that's going to be wood block. All right, so the solve for the final velocity of the wood block. That's going to be part A. Part B, we need to ask ourselves, what is a force bringing block to rest? Okay, and how do we find that? I think you know what the force is. The force is friction, right? The block will keep moving forever, and friction doesn't slow it down. But we need to go back to our resources of what friction, what kind of values go together to create friction, and we're going to need to incorporate that in part B. And C is really the question that's being asked at the end of the question: how far does a block move? Or does a block slide? All right, that's block is W right there. Okay, so we're going to do these in kind of a step-by-step basis. And so you should, basically, we're going to be solving for this, but giving you little baby steps, I think, will make more sense and kind of have it be more logical for you. All right, so I'm going to take this and I'm just going to, let's see here, I'm going to take all this and just shrink it down. There we go, and do that right there, okay? In fact, yeah, that's fine. Okay, so we've got a bullet traveling at some speed, all right? So it's doing that, all right? And I'll put the ground right here. Let's see, we'll do this. All right, and the bullet is traveling towards a block which is at rest. Okay, and then kapow, there's a collision. All right, and afterwards, the bullet keeps on traveling through it. The bullet got longer and skinnier for some reason. Bullet's traveling through it at a reduced speed, but the block also is moving as well. Okay? So we want to find what all these values are right here. Well, the guiding principle behind solving for this is the idea that momentum is conserved. Momentum, all the momentum initial equals all the momentum final. All right, so we can say that momentum of the bullet, or initial momentum of the bullet plus initial momentum of the block, is going to equal the final momentum of the block and plus the final momentum of the bullet. Okay. So that's going to be mass of, I've got a menu right here that I want to get out of the way. Let me see if I can move some stuff around a little bit. There we go, that's a little bit better. All right, so mass of the bullet times velocity initial of the bullet plus mass of the wood block times the velocity initial of the wood block, which already you know what's going to happen to that, right? Because the initial velocity of that is 0. Is going to be equal to mass of the wood block times the final velocity of the wood block. That's what we're solving for, right? Plus mass of the bullet times the final velocity of the bullet. Okay? That's what we're looking for right there. So we want to solve for what? We want to solve for this final velocity of the wood block right there. So let's rearrange everything and solve for that. All right, what I'm going to do is I'm going to subtract this whole thing over to that side, right? And then I'm going to divide everything by that mass of the wood block right there. So we're going to get this. Oh, I don't want to do it in red, though. I'll do it in blue. By the way, this is all part A. All right, part A is asking us what is the final velocity of the wood block right there. Final velocity of the that's a B for bullet, of the wood block is going to be mass of the bullet times initial velocity of the bullet minus, we're going to subtract this to the other side, minus mass of the bullet times the final velocity of the bullet. And all that gets divided over this right here, mass of the wood block. All right? So mass of the bullet, what do we have? 0.075 kilograms. And I got a feeling I'm going to run out of space here real quick. Times how fast is it moving initially? 450 meters per second. All right? Minus mass of the bullet, 0.075 kilograms, times what's our new velocity after it's exited the block? That's 125 meters per second. All right, all that divided by the mass of the block, which is 2.25 kilograms. 2.25 kg right there. So the final velocity of the wood block is going to be what? I get a value of 10.8 meters per second. All right, let's dotted line box that because that's not our final answer, but it's very important to getting our final answer. All right, that's all part A right there. Let's do part B in, let's see. I'll do that in a different color. I'll do that in green to kind of to make that stand out a little bit. All right, part B is asking, well, according to my step-by-step, we're asking, what is the force bringing the block to rest? All right, because now after the collision, the block is moving, so is the bullet. The bullet just travels on and lands somewhere, but the block is going to be sliding along this tabletop. And this tabletop has friction on the surface. So what's going to be bringing the block to rest? Well, the force of friction is going to be doing that. And we know that the force, and nothing else is going to be doing that, just the force of friction, sliding, scraping across the tabletop. We know that the force of friction, or the force of kinetic friction, is, first of all, it's always negative, right? Because it always acts against the direction of motion. Negative what? Mu k, that is our coefficient, times mg. That's our force right there. That's bringing it to rest. So we have the mu k, we have the mass of the block, we have g right there. It should be pretty easy to just to solve for what that force of kinetic friction is. So 0.2, that's our mu k, right? Our coefficient, times 2.25, that's the mass of the block, times 9.81, that's 4.41 newtons. Actually, I should say negative, right? Negative 4.41 newtons. That's what's bringing the block to rest right there. All right, lastly, I'll do this in, I will say orange, okay? C. It's really asking us, how far does the block slide? Okay, or what is that distance that the block slides right there before it comes to rest? All right, now this isn't a momentum issue anymore. This is a what kind of issue? This is an energy issue, right? Work and energy, because this force of friction is being applied to the block over some distance d, which we don't know. And what that's doing is taking the energy out of the block and bringing it to rest, right? Let's say, what's the initial kinetic energy of the block? All right, well, that's 1/2 m times the velocity of the wood block squared. That's this velocity right here that we solve for. Okay, that's how fast it's moving when it starts, when the bullet makes it move. That's that velocity. Okay. What's the final kinetic energy? K final. That's going to be 0, right? 0 joules because it's coming to rest. So what's bringing it to rest? The non-conservative work done by friction, Fr right there, or I should do Fk, by kinetic friction. That's what's bringing it to rest, all right? Work is a force applied over a distance. So that's the friction force times that distance. Hey, that's what we're looking for right there. That's that. So there, if we put all this stuff together, we should be able to find what that distance is. All right. So how do we state the energy in a system before and after something happens? Well, the change in energy final equals energy initial. And if all the energy is conserved, they add up. But if you have some non-conservative work or non-conservative energy going on, that has to be added to the final energy. All right. In this case, the work that is done is negative work. We've got this friction acting against us right there. So that's actually got to be subtracted from that to give us our final energy. All right. Well, our final energy is 0 joules. Okay. And what's our initial kinetic energy? Our initial energy? It's kinetic. Our kinetic initial right there, which is that. And we know what all those things are. We know the mass of the block. I should put a little W right there. Mass of the wood block. And we know the velocity of the wood block after the bullet exits it, right? So we should be able to do that plus the non-conservative work. All right. The non-conservative work is actually negative, right? So what I'm going to do is I'm going to just, since this side right here is 0, I'm going to just bring that to that side. So we can say the non-conservative work that is done equals the initial kinetic energy. Okay? Let's see here. You know what? I don't want to mess with our signs right here. I'm going to do this. I'm going to do the negative kinetic energy initial equals the non-conservative work that is done. All right, and it'll make sense why that is in just a minute. All right, negative, what's the initial kinetic energy? 1/2 mass times initial velocity of the wood block squared, right? Equals, what's our non-conservative work? That's negative mu k times m times g times d right there, right? That's the work that is done because you've got this force, friction, times the distance. Let's just solve for d and plug in what we've got. All right, so d, what do we do to solve for d? We're going to divide this down below everything else, right? So that's 1/2 mass times the velocity of the wood block squared divided by, oh, there should be a minus out front there, minus mu k m g. Well, you can see right now that the masses are going to cancel out, right? It goes away right there, and that goes away. So we have the distance is the initial velocity of the wood block squared divided by 2 mu k times g. That really got squished down there at the bottom right there. So what's the initial velocity of the wood block? That is 10.8. 10.8 squared. I'm going to leave my units out for simplicity's sake. Times 2 times what's our coefficient of kinetic friction? It's 0.2 times 9.81. And that, my friend, should give us our final answer of distance. All right, what do we get for that? I get a grand total of 29.7 meters. That's how far it's going to slide. All right, so we're incorporating some elements of, well, right here we've got conservation of momentum. Here we've got some elements of friction. We need to know how to find that friction force, right? Here is elements of conservation of energy, all right? Final energy is initial energy plus whatever non-conservative work was done right there. We wrote them out in more detail, solved for what we didn't know, plugged in our values, and we have our final answer right here. So that's example 10.8. Each of those steps you should be able to do. It's just a matter of putting them all in the right order and being able to execute. All right. So there you go, example 10, 8. If you have any questions, make sure you come see me. Otherwise, thanks for watching. I'll see you on the next one.